Okay, let's start. Good morning, everyone. I'm Jingzhu. Today, I'm going to present our work, Artemis. SSRF vulnerabilities are inevitable in PHP web applications. These applications often use server-side requests to communicate with third-party services. However, the attackers can exploit this by making it look like the server itself is sending the request, allowing them to bypass access controls like firewalls that normally block direct access to certain URLs. Exploitation of SSRF vulnerabilities can lead to severe consequences. For example, in 2019, an SSRF vulnerability in Capital One's service led to the exposure of credit card information for over 100 million customers. Since 2021, SSRF has been ranked as the top 10 vulnerability by OOPSLA'25. Currently, PHP is a dominant programming language for building web applications, and developers have limited experience to avoid SSRFs. Static Taint analysis is commonly used to detect vulnerabilities in PHP web applications. To illustrate the idea, let's look at a new SSRF vulnerability. The application takes the user input from the post function, and we mark it as a source. This input eventually reaches the request sending function curl_set_opt, which we treated as a sink. Our goal is to determine whether there's a feasible path from the tainted source to the sink. However, the analysis becomes tricky because the call flow is hidden by a dynamically assigned class name, RSS file class. Existing static tools fail to build a complete call graph. Another issue is that these tools often ignore path conditions inside if statements. In this case, a feasible path only exists when URL variable is not empty and contains the substring block spot. We observe 4 key challenges in the existing tools. First, third-party sources and sinks are ignored. Second, both explicit and implicit call targets are used in PHP applications. Third, there exist either over-tainting and under-tainting rules. Fourth, infeasible paths are reported because of ignoring path conditions. In our paper, we design and implement a new static taint analysis tool called Artemis to detect SSRF vulnerabilities in PHP applications. Artemis has 4 modules. First, it extracts both PHP's built-in and third-party sources and sinks. Second, it builds explicit and implicit call graphs while handling PHP's dynamic typing. Third, it performs taint analysis to find possible paths from sources to sinks, using enhanced propagation rules. Finally, Artemis reduces false positives by analyzing path conditions and removing any infeasible paths. For source and sink identification, Artemis identifies them from both PHP's built-in and third-party libraries. We identify built-in sources and sinks following previous work. For example, we treat get and post as sources because they typically take user input from incoming requests. For built-in sinks, we include functions that access files or send network requests. For third-party sources and sinks, Artemis focuses on public functions with PHP doc comments because those functions are intended for external use. Then, we use few-shot learning with GPT-4o to classify whether each function is a source, a sink, or neither. To make sure the results are accurate, we manually verify the extracted sources and sinks. To statically construct a call graph, Artemis identifies both explicit and implicit call targets. For explicit call targets, Artemis matches method call signatures. Specifically, we look at the class name, the method name, and the parameter counts and types. The last 4 call types correspond to implicit call targets. When the method and class name are known but the method isn't defined in the class hierarchy, Artemis treats it as a magic call and searches for PHP's magic method. Specifically, we check call and call static along the inheritance chain. For example, the method call client wrapper get doesn't match any defined method in the client wrapper class. However, since the call static method exists, Artemis recognizes this as a magic call and builds the corresponding call flow. When a call target has a known method name but a variable class name, Artemis searches through all building and application classes to find the method with the same method name and the same parameter count. If no matching method is found but the class defines the magic method, Artemis treats the magic method as a possible call site, regardless of its parameters. When a call target has a known class name but a variable method name, Artemis searches all methods in that class and its class hierarchy. Any method with the same parameter count is treated as a potential call target. Moreover, all magic methods in those classes are considered candidate call sites. When both the class name and method name are variable, Artemis searches all methods across all building and application classes. It looks for the method with the same parameter count and compatible types. Moreover, Artemis considers magic methods without parameter checking. Third, Artemis performs rule-based taint analysis to track how tainted data flows through the call graph. We design a set of propagation rules to handle common PHP operations. To improve accuracy, these rules are carefully designed to reduce both over-tainting and under-tainting. For general cases like variable assignment, unary or binary operation, and typecasting, Artemis follows the same rule used in state-of-the-art approaches. When Artemis encounters a branch like an if-else statement, it uses a fine assignment rule to merge the states coming from different branches. When a method is called, the program's state moves from the argument to the method's parameter, flows through the method's statements, and then returns to the caller via the result. When initializing an array, Artemis records every element's state based on whether the index is known. It tracks individual elements, not whole arrays. When Artemis says a for each loop, it marks the loop variable as tainted if every element in the array is tainted, or if the array is partially tainted but the loop body has no branch. For example, the array URLs comes from post, which is the tainted source, so URL is tainted. Inside the loop, image URL is created from URLs, so it's also tainted. We also handle implicit data flows that arise from PHP's dynamic features. For instance, the built-in extract function creates variable from an array. When Artemis says extract, it synthesizes explicit assignments so the data flow is tracked. Finally, to prevent over-tainting, Artemis uses safety string assurance. A string is only considered tainted if it can actually control the file or request the URL an attacker could use. So, if a variable controls the IP or requests the URL, it's tainted. Otherwise, it remains untainted. So far, the rule-based taint analysis is path insensitive, which can produce false positives by reporting invisible paths. The fourth module helps reduce this by pruning two types of false positives, which are always unsatisfied conditions and URL rejection conditions. Given a taint propagation path, Artemis extracts path conditions from each function or method's control flow graph. It then prunes unreachable paths because their conditions are never satisfied. For example, if the variable service has mismatched values which are maximind and fragile IP, Artemis recognizes this as a false positive. Artemis also prunes false positives caused by string checking conditions. To do this, it first identifies common string checking functions like strpos and pragmatch, and translates these checks into string conditions. Then it uses an SMT solver to see if any valid URLs can satisfy all the constraints. For example, if a path uses strpos to check a string, Artemis models this as a constraint and also models valid URLs with regular expression. The SMT solver can then show that no valid URL can satisfy all the constraints, so the path is marked as a false positive. We have implemented a prototype of Artemis. For the benchmark, we select 250 applications based on 2 criteria. First, we collect 55 vulnerable applications from the CVE database to evaluate whether Artemis is able to detect known vulnerabilities. Second, we gather 195 popular applications to assess Artemis' ability to detect new vulnerabilities. We compare Artemis with 5 static taint analysis tools for PHP. In total, Artemis identifies 207 true positive paths, corresponding to 106 true positive vulnerabilities. Among the 106 vulnerabilities, 35 are newly discovered. We have reported them to developers, and 24 have been assigned with CVE IDs. The evaluation results also show that Artemis significantly outperforms existing tools in both true positives and false positives. To evaluate the impact of each component in Artemis, we conduct an ablation study, systematically removing one module at a time to see how it affects detection performance. All the key results are highlighted here. To conclude, we present Artemis, a static taint analysis tool for detecting SSRF vulnerabilities in PHP web applications. Artemis has 4 modules that work together to improve true positive detection while reducing false positives. In our evaluation, Artemis discovers 207 true positive paths corresponding to 106 vulnerabilities, including 35 newly discovered ones. That's all for my talk. Thank you for your attention.
Get the floor started, warm up those questions. Really impressive sort of complete work on like these PHP vulnerabilities, and certainly very important with these new CVEs. I wonder if you could talk a little bit about the lessons that you might have learned that could make this more applicable to other languages, or how much of what you've done here is very specific to PHP, how much are lessons that we can take to other languages?
Yeah, very good question. Actually, in our work, some modules are specific to PHP language, like the core graph construction, because the PHP has some dynamic features like magic methods. Actually, maybe in other dynamic languages, they also exist some similar features. We will investigate them in the future. Let's say whether those features can lead to severe vulnerabilities like that. And also, some features are specific to SSRF vulnerabilities only, like the modules like we do the false positives. I believe that this framework is not so specific, and we can extend such similar frameworks to other languages, to other vulnerabilities, and to build secure software systems.
I had a quick question. Good talk. It's a good tool, it seems. So the source sync identification that you are doing using the LLMs, what if the LLM finds an invalid source sync pair?
Invalid source and sync pair. We don't care about the pair. We only care about whether the sources are true sources and whether the syncs are true syncs. We don't care about the pair.
invalid source or an invalid sink?
We manually verified. So after we use GPT-4o, actually there contains only a few false positives, maybe 2, 3, something like that. In total, we have, as I remember, we have 42 sources and 40 sinks. Those sources and sinks, we have carefully manually verified them. Yeah. Thank you.